students, welcome back again. In this part we will discuss about terminology used in simple harmonic motion, and then we will discuss about systems of SHM. In the first part we will discuss about how we will get time period of a simple pendulum. So let's begin. Let's begin with the terminology used in simple harmonic motion. The first terminology about amplitude. What is the amplitude? Amplitude is actually the maximum displacement of the SHM from the equilibrium or mean position. That is called as amplitude. So it is just the maximum displacement from the mean position, and it can be represented in meter, means its SI unit is meter. Period is just time taken for one complete cycle, that we can see here. Now we can say frequency. Frequency is just the number of cycles in one complete revolution is called as frequency, and its unit is hertz, or we can say per second. Angular frequency is just the angular displacement upon time t for one complete revolution. Its unit is radian per second. So these are the terminology used in SHM. Also we have wavelength, energy, amplitude, mass, or wave constant, that is spring constant k, or we can say wave displacement constant, that is k also. Now in the next part we would like to discuss systems of SHM, the very important part involved in SHM. So we must know, when we are talking about systems of SHM, for the first case we will discuss about simple pendulum. In case of simple pendulum, we would have a block, we would have a bob of mass m that is connected with a light string that execute to and from motion about the mean position. So what? A simple pendulum is pulled slightly to point P, extreme position or some displacement. The string makes an angle theta to the vertical and the arc length x shown in the figure. The forces, now we would draft the free body diagram, or we can say we will draft the force that brings system towards the mean position. So mg acting vertically downward, mg cos theta is just the radial component, mg sin theta is the restoring force acting over here. So tangential component mg sin theta, radial component mg cos theta we can see, and t is the force in the string, that is a constant force. Now after this we would like to discuss the resultant force in the radial direction provides the centripetal force which enables the bow to move along the arc and is given by T minus mg. So means we can say if at any moment T, and that is just mg cos of theta, so that is equal to the centripetal force Fc. That's why we write T minus mg cos theta equal to mv square upon r equal to Fc. Now we would like to draft equation for restoring force, that is mg sin theta, this way. So we are getting Fs is equal to mg sin theta over here. Negative sign means restoring force is always in opposite direction of the displacement. Now next point we would like to do for the small displacement, as theta sin theta will be equal to theta, so we will calculate sin theta is equal to x by L or theta is equal to L. So Fs is equal to minus mg x by L. So this would be the net restoring force, that is minus of mg x by L. So we are getting, applying Newton's second law of motion, that net force should be equal to mass into acceleration, that should be equal to force, restoring force. Now in the next slide we would like to discuss here the terms involved. So in this, that ma is equal to, so means in case of restoring force we know that Fr is equal to mass into restoring acceleration, that is always equal to mg into x by L. So we are getting restoring acceleration is equal to minus of g by L into x. So we wanted to prove this because when the restoring acceleration is directly proportional to negative of the displacement from the mean position, we got the condition for SHM. On comparing, we got A is equal to minus g by L into x, where A equal to omega square into x, because we have the standard equation 2. On comparing this equation with the mean equation, we get omega square equal to g by L equal to omega 2 pi by t. So on solving this we get t equal to 2 pi under root L upon g. So different cases are there because t equal to 2 pi under root of L upon g effective. Means we can have different application for the case. If we have a car that is in static situation and it is its simple pendulum is in motion, we will calculate G effective is G. But when it is under lift is going vertically upward. So with its frame of reference, we will calculate G effective. So it would be G plus E. If lift is going vertically downward, it would be G minus E. Third case, if car is moving at certain angle or it is in a turning point, so what we will calculate, because there is radial acceleration and also downward gravity effect, so we will calculate A square plus G square. That would be the G effective. Fourth case, if we bring system on any planet, so we will calculate the acceleration of that particular planet. Or many cases are involved, like case of rotational simple harmonic motion. In that case, we would like to calculate, the first condition should be involved, draft the equation of force or torque at mean position. Now, you apply some force, the system would like to oscillate. Now, we will calculate the condition for restoring force or restoring torque. That should be equal to I into alpha. I is the moment of inertia, omega, so alpha is the angular acceleration. So we will calculate the net torque, that is just the restoring torque, and we will proceed in this way. Third method can involve energy conservation law. We will calculate total energy before the restoring condition and total energy after the condition. So we will differentiate this relation and we will get a condition for force. So finally we are interested to know the angular frequency, that is a function of acceleration, that is A equal to minus omega square into x. So in this way we can calculate time period for different cases. And very important part involved in case of rotational simple harmonic motion, like a rod is connected with two springs. If on applying small jerk to that system, what happens? Rod execute simple harmonic motion. So we must know what is the center of rotation, oscillation. So mean if there is a rod of length L, it would have moment of inertia about the same time L square by 12. If one spring is connected at top, another spring connected in this way. So what will happen means due to these two forces, the restoring force will be twice of kx. Now we will calculate torque about the mean position. So 2kx into L by 2 should be equal to I into alpha. In this way we will calculate our time period. Third case, if there is a ring or there is a sphere, a spring is connected at top. So what happens if you are giving small jerk? What happens? Rotation take place. Means what happens in that case? Means due to that spring will provide sufficient torque to that rod or to that sphere, and that's why that sphere would be in oscillating situation. So due to that oscillating situation, we would be in condition to calculate net restoring torque should be equal to I into alpha. And always keep in mind moment of inertia about the axis of rotation. So means center point is the axis of rotation, like that. Because we are not calculating its rotation about the center point, we have to calculate its rotation about the point of contact with the ground. So there are different cases for that. We can calculate simple harmonic motion equations. Now we would like to proceed for a question, that is, a certain simple pendulum has a period on Earth's surface, time period t equal to 1. So we would like to calculate t on the surface of Earth is given as t equal to 1.6 second. 1.60 second. Determine the period of the simple pendulum on the surface of Mars. If gravity means we have to complete on Mars. If gravity on Earth is given as 9.8 meter per second square and gravity of the object on Mars is equal to 3.71 meter per second square. We know that in case of simple pendulum t equal to t2 by under root L upon G effective. So we are knowing t on Mars upon t on Earth is equal to under root of, they are inversely proportional to each other. That's why G effective on Earth upon G effective on Mars. So that's why under root of 9.181 upon 3.71. So on solving this mathematical equation, we will get the value would be around 2.61 second. So means because T mass is equal to the value of this we are getting, and 9.81 upon 3.71 into time of that is would be around 2.71. In this way we will get the answer of this question. So what we have done, we use the simple equation for time t equal to pi L upon g, and we will proceed in this way. Ask IITians brings you a very good opportunity to paste your questions regarding the subject. What you need to do, first of all, select www.askiitians.com, then choose Ask a Question link. After that, you will reflect a discussion board where you can post your questions. After that, you need to go for select category. If you want to paste a questions regarding electrostatic, choose the concerned link, then type your question. After typing the question, select get answer. Then you will find the answer of your question within 24 to 48 hours. In this part, we discussed about terminology used in SHM along with the systems of SHM, and we calculated time period of a simple pendulum. I hope you are enjoying for calculating time period of different SHM. Now, in the next part, we will discuss about time period of a spring mass system in vertical as well as horizontal situation along with the spring connected in series as well as parallel. So stay tuned with us.